Okay, let's take a look at an example, and I'm going to choose one out of the book um, because I haven't done one of these by hand forever. So we'll see how this goes. Um, okay, example 9.1: a study using two random samples, 35 people, blah, 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 blah. Okay, I'm looking for my claim. Okay, can it be concluded there's a significant difference in the average time each group spends on leisure activities? Significant difference. That means they're different, not equal. So that sounds like our claim. Okay, now the question becomes which one do you put first? So our claim, that's nice. There we go. Okay. Boy, that's not working very well. But I want something not equal to something else. Now, oftentimes when you read it, the first one you run across is your first population first sample. This is kind of a standard you can go with. A study using two random samples, 35 people each, found an average amount of time of those in the age group of 26 to 35 years spent per week on this and those. Okay, so we got two age groups. We got young age group and the old. So I'm going to say since 26 to 35 was first, 26 to 35 was first is not equal to, different than, 46 to 55. Your first reading of a problem should be to identify your claim. And then, unless it tells you differently, you can assume that this is your first population, first sample, and this is your second population, second sample. That's going to become important. Now, for this problem, I'll read a little closer now. A study using two random samples of 35 people each. So the number of people in each group. So I got 26 to 35. That's my first population, first sample. And I got my 46 to 55. That'd be my second population, second sample. And this would be N1, and this would be N2. And I think they're both 35. Yeah, both 35. And each found that the average amount of time those in age group spent per week. Okay. So for the average amount of time for those in this group was 39.6. So that's our X bar. This is referring to the sample. So this is X bar sub 1 is equal to 39.6. Oops, let's try it again. And let's see, an age group of 46 to 55 spend 35.4 hours. So 35.4 hours. Assume the population standard deviation for those in the first age group found by previous studies is 6.3 hours. So that's sigma. Sigma 1 was 6.3. And sigma 2, again, it says population standard deviation. That's what's telling me sigma. Of those in the second group was 5.8. So it's 5.8. Alpha is 5%. Can it be concluded a significant difference in the, okay, so that's everything they give us. Okay, now this is the classical approach. It's easiest when you do it by hand. I'm going to modify this slightly to go with our example. Write down a shortened version of the claim. We did that. Come up with a null and alternate hypothesis. H naught always has the equals part on it. So, and I'm going to refer to this, since we're talking about the mean, this will be mu sub 1, and this will be mu sub 2. Well, where we put that in is an H1, so this would be mu 1 is not equal to mu 2. The only symbols you can put on H1 are less than, greater than, or not equal to. And the convention that most books, and I don't remember about Blumen, that most books go to is the only symbol you can put on H naught is an equals, which works out well here because these you can think of as opposites each other. So the opposite of not equal is equal. Step 3, see if your claim matches H naught or H1, and it's based upon a symbol. This is a not equal, here's a not equal. So our claim matches H1. And we'll come back to that. Step 4, draw the picture, and it's based upon a symbol off of H1. H1 is a not equal to, that tells us two tails. Draw the picture and split alpha into the tails. Now alpha is 5%. I got two tails, left tail and right tail. So I'm going to take that 5% and divide it by 2. And I put that in my calculator. 0.05 divided by 2, I get 0.025. And if 5% is in the tails, that means 95% is going to be the main body. Okay. Find the critical values. Now this says t-distribution table. Problem with that is, this is out of a different book. Problem with that is sigma's known. And if I look in the book, find the critical values. That's really nice. Why would you not say how? And still didn't say how. But when you're performing the z-test, and this is a z-test because we're given sigma, then you'd use the standard normal distribution table in the back of the book. Let me think how to do this. I thought the bookmark would come up here, but I guess not. Okay, well, I'll come back. I'll come back to that. Standard normal distribution table. And okay, good. They have the picture down here, and the standard normal distribution, unless it says otherwise, is pretty much always the area to the left. But I wanted to verify that. There was one book I used one time that was the area to the right. Okay, so area to the left. If I want to find this left critical value here, the area to the left is 0.025. Okay, so okay, let me think about this. Okay, we're looking it up in the middle. It's been, like I say, it's been a while since I've done this by hand. That's random numbers. So I'm going to look up the value that's closest to 0.025 in the middle of my table here. And here's one that's exactly 0.025. Perfect. So I come over to here, that gives me my first part of my number, negative 1.9. I come up here and that gives me my hundredths place, 0.06. So I'm going to have negative 1.96. Negative 1.96. Now for this one, the area to the left of this one, you have to add up all of this, 0.025 plus 0.95. So I'm looking for 0.975, the two added together. And here's 0.975 right here. If I go clear to the left, that gives me 1.9. If I go clear up, I can't see it. But if I go clear up, that would give me my 0.06. So this is going to be a positive 1.96. So same idea here. We find our critical values, but when we're given the sigmas, then we have to use the normal distribution table, the z values. Then step 6 says to find the test statistic. And that's a formula out of the book. So let me go back to chapter 9. And oops, what in the world? It would bounce around. Here's my formula for the test statistic, and I give you that an example down here. See how they got x bar sub 1 minus x bar sub 2 minus mu sub 1 minus mu sub 2, and so forth. Okay, now where was it at? This right here. Of course, to use this formula, you have to have sigmas. So if you're given s's, some books have a different formula. I don't think I saw it in this book unless it's in the next section. And I don't think wait a minute. What's this one say? Testing the difference between two means of independent samples using the t-test. So this one is specifically the z-test. Okay, so z is equal to x bar sub 1 minus x bar sub 2 minus mu sub 1 minus mu sub 2 over square root of sigma sub 1 squared over n1 plus sigma sub 2 squared over n2. Now we're actually testing the difference between the mu's here, and so typically you will not have the mu's, so those are always 0. I shouldn't say 0. There'll probably be the oddball problem where they give you the population mean of both of them, but typically you don't have those and you go 0. Okay, so x bar sub 1 is 39.6 minus x bar sub 2, which is 35.4, minus 0 over square root of sigma sub 1, 6.3 n squared, divided by n1, which is 35, plus sigma sub 2, which is 5.8 squared over 35. And let's see here. 39. Oops. What in the world? Stupid calculator. Okay. 39.6 minus 35.4. And the zeros I can drop away. Divided by square root of 6.3 squared divided by 35 plus 5.8 squared divided by 35. Of course, if you got a scientific calculator, put that in however you can. Every calculator is different in that regard. I don't know how many decimal places. I'll take two decimal places, 2.90. Okay, now before I go on, let me double check that against the problem. See how far off I am. 2.90, negative 1.96, positive 1.96. Okay, perfect. Now that was my test statistic I just found. So, this last step, you have to think of this as a number line here. So here's a number line, here's negative 1.96, here's positive 1.96. Your test statistic, you have to decide if it falls over here, over here, over here, number line wise. It would fall over here, number line wise, so it falls in my tail. This says if your test statistic falls in your tail, you reject H naught. So we'll reject H naught. Now H naught and H1s are opposites each other, so that means I'll accept H1. The books use a different terminology for that. They say do not reject. But I find students click better if I say reject and accept. But realize that most books will say do not reject, which is kind of the same as accept. Now, since our claim matches H1, whatever we say about H1 is what we say about our claim. We accepted H1, which means we'll accept our claim. Now, while we're talking about it, that's how you do it by hand. If I were to go on to the next section, 9.2, it's exact same steps. The difference is to find the test statistic, use this formula, which looks very similar, doesn't it? You'll find that if you incorrectly identify the standard deviations, you would still get the correct test statistic here. But your critical values, I'm not sure if it says it here, but for your critical values, you have to use a t-distribution table. Okay, here's what we're talking about. Find the critical values. Since test is two-tailed and alpha is equal to 0.05, the degree of freedom are the smaller of n1 minus 1, n2 minus 1. So you take your smaller sample size. So for like here, random sample 9 men, so that's 9. Random sample 7. So my smaller sample size is 7 women. So my degree of freedom will be 7 minus 1 or 6. So I'm going to look up 6. And let me write this down because I'll forget it. This one appears to be 2 tails. So my degree of freedom is 6. I had 2 tails. Alpha was 5%, so 0.025 in each tail. And let's go look at how to use a t-distribution table, though you probably know how to use it from the previous chapter. T-distribution. Okay. Now, this is referring to the degree of freedoms over here on the side. And then we got our 1 tail here, or 2 tails. For the amount in 1 tail is 0.025. So if I come over to the column for 0.025, it's right there, which happens to match the amount in both tails is 5%. So we're going to be looking in this column, and I'll come down to degree of freedom of 6, and that tells me 2.447. Both of these are 2.447. The difference is, whenever your critical value is on the left side, you always put a negative on it. Okay, now let me go back and double check that to make sure I got that right. Okay. Did I go to the right place? Okay, 2.447, negative 2.447. Okay. So that's how you'd find the critical values. Other than that, it's exactly the same steps as what you see right here. That should help you on those 2 sections on doing it by hand.